Hello guys, welcome back to another lecture. In this lecture, we're gonna, explore a very important topic about, processors, which is called pipelining. So pipelining is basically a way to enhance or improve the speed of the processors. So what's pipelining basically? It's a way to pipeline data or execute data but in parallel, a form of parallel, parallel execution, in which we have multiple elements, and or multiple, circuits, we can say, or the processor divided into multiple circuits, and each circuit is and all these circuits are working at the same time in parallel, basically. So to give you an idea about pipelining, let's take, an example from a laundry. And we're going to take time in this example because this is a foundation example. Once you understand it, then you're going to understand basically how pipelining working in processors. So let's say that your laundry, takes 4 stages, basically washing, then drying, folding, and finally putting the clothes into the closet. So you have 4 stages to make your laundry, okay? So let's assume, for example, each one of these stages takes half an hour. So the washing in the washing machine takes half an hour. The dryer takes half an hour. The folding takes half an hour. The putting the clothes into the closet takes another half an hour. So one operation or one user takes 2 hours. Okay, takes 2 hours. Then if you, with no pipelining, if you have 4 users or 4 loads of clothes, then you're gonna have 8 hours to complete the laundry for 4 users. But if we look here, once the for user A, once it moves its clothes into the dryer, then the washing machine becomes empty. So why not user B use the washing machine while user A is using the dryer? Because it was empty. That's very intuitive. And once user A start to fold and fold its clothes, that means the dryer becomes free now. User B can use the dryer. At the same time, user A is folding, and then since user B has left the the washing machine, then user C can start using the washing machine. And if we do that, we're gonna see that we're gonna simply that we take just 3.5 an hour. Just count it: 1, 2, 3, 4, 5, 6, 7. 7, and each step of those is half an hour. Then we take in total 3.5 an hour. So we reduced the time from 8 hours into 3.5 hours only. So the speed up here is around 2.3. The speed up is just divide the higher or the longer time or over the pipelining time. That's basically pipelining. Okay, that's basically pipelining. And let's assume now that we have 5 users, A, B, C, D, E. So the 5 users with no pipelining will take 10 hours, because each load or each user takes 2 hours. And with pipelining, this will be 4 hours. That's basically 2.5, which is more than 2.3. Well, the speed up now increases, improved, because the number of users increased. That's with 5 users. With 6 users, it will be 12 hours in series with no pipelining, and 4.5 hours with pipelining, which is basic 2.66. And as you increase more and more the number of users that use the same stages and make pipelining, you're gonna see that the speed up is increasing until it reaches at infinity, which is a theoretical value, of course, 4. Okay, so the cap, our cap is 4 here. And you can, deduce a general form for the speed up in that way. So for n users, with no pipelining, we need 2n hours because each user takes 2 hours. So for n users, basically it's 2n hours. For pipelining, let's decimate it into in very detailed, so you can understand we can basically find a general formula for it. So if you have just one user, this will take 2 hours. So no, there is no saving here, because one user also with no pipelining will take also 2 hours. But with 2 users, then look at it. One user takes 2 hours, but for 2 users, part of the execution time of the second user is hidden with the first user execution time, and you only increased the total time by half an hour. So this is basically 2.5 an hour, because we started here and we ended here. With 3 users, which is basically, we can say it's 2 plus half an hour. For 3 users, you have 2 hours for the first user, another half an hour to the second user to finish, another half an hour to the third user to finish. Again, 2 hours, then half an hour, then another half an hour, which is basically 3 hours. And so for 4 users, it will be 3.5. 5 users, 4 hours, and so on, and so on. So we can say it's always 2 hours plus n multiplied by half. I'm sorry, n minus 1, not n. I'm sorry, this is n minus 1. So the rest of the users, which is n minus 1, will take half an hour. So the first user takes 2 hours. This is clear, a clear 2 hours. But the other users, n minus 1, their delay is basically can be high, is hidden because of the pipelining. And if you divide this 2n by 2 plus n minus 1.5, this will be the speed up general formula. And if n goes to infinity, limit n goes to infinity for a very high number of users, this will be 4. The speed up will be 4. Just I'm gonna let it for you as a as a practice to find this general speed up for infinite users. Okay, guys, we're gonna apply basically the same principle into our microprocessor. Okay, either x86 or any other type of processor. Basically, most of the processors nowadays, and actually this is from the past, use pipelining, and still it's a very essential component for any processor produced nowadays. So here is an example now for let's now concentrate about how to apply this into a processor. In a processor, we have instructions. Okay, so some of these instructions is independent on each other, and some of them is dependent. So with no pipelining, if we have 3 instructions like this, and each one, for example, takes 1 cycle, then we're gonna use 3 cycles. But with pipelining, we can, if we have basically some circuits that can execute each instruction in parallel, this will take 1 cycle. At the same time, we can execute this, but this guy, the third one, is dependent on 2 and 1, because E is equal to A plus B, completely independent from the second instruction, which is F equal to C plus D. But G is dependent on, needs the F value and the E value. So it must wait. So we're gonna execute these 2 guys at the same time. Then in the second cycle, we're gonna execute the third instruction. So we use the 2 cycles here. This is called instruction level parallelism, ILP. The ability or the, a kind of measure of how many instructions can be executed simultaneously. Okay, and in that case here, because of the dependency, it's 2 cycles. If all of them are independent, then you can execute them at the same cycle, all of them, then you're going to execute all of them in just 1 cycle. So we have a speed up of 3. Okay. Types of pipelining, it's based on the application is that you have. So for example, for graphics or graphics processing cards, GPUs, you have many operations that you can or have many processes that you can do on an image or a video. So if you have different circuits in your GPUs that can handle these processes at the same time, you can, for example, have a circuit that running or processing window clipping, another circuit at the same time processing color and light calculations, another one making rendering, all of this at the same time. And softwares, again, if you have parts of your software that are independent from each other, then these 2 parts or 3 or whatever can run in parallel. And finally, our focus here is about instructions. If you have independent instructions, these instructions can work in parallel, and this will make a huge speed up for your processor. Again, to apply the pipelining in your processor, instruction pipelining, you must divide your processor circuit into multiple circuitry, and then you start to use, or you make your best to use all these circuitry at the same time. So one example or one practical example is the 5-stage pipeline, in which you have your processor can be divided into 5 stages, basically instruction fetch stage. So here is an example of a processor. You don't need to memorize this sketch. This is just for illustration. So in the instruction fetch, or simply fetch, if you fetch the instruction from the memory and put it on the data bus here, on instruction bus. Then another circuitry, which is for decoding. So you need to know what this instruction is. Is it subtract? Is it addition? Is it jump? Whatever. So there are many instructions in assembly, as we saw. So we need to know, another circuit need to know what this instruction is. And at the same time, if this instruction will use some of the registers, we need to read these registers. So the second stage, or the second circuitry, or the second part of the processor is called instruction decode, ID, or simply D. Okay, in which you're gonna decode the instruction to know its job and read the required registers, if any, of course. After you know what is an instruction and its parameters or registers, you execute it. The third circuitry, this part, is for execution. That's why here you have, for example, ALU, arithmetic logic unit. You might have, for example, addition or subtraction, whatever. Then after the execution, you might have 2 operations. You might update some location in the memory, like, for example, making add, BX and AL. In that case, you are saying that the location that's pointed to by BX will be updated or added to the value of AL, and then put the result in BX, this memory address. So in that case, you need memory access, or you might have something like this: add AL BL, which is AL equal to L plus BL, and in that case, you might you will need to update the register value AL. So in the final stage here, we have what's called the write back to the register files, basically. So these are 5 stages, and here is how the pipeline work. Basically, if you have 5 instructions and everything is perfect, these instructions are independent, then once you fetch the first instruction in the first cycle, then in the second cycle, this instruction will be decoded and the fetch circuit will be free. So at that time, you can fetch the second instruction. So in the first instruction, we make the fetch. In the first cycle, we make the fetch of the first instruction. In the second cycle, the first instruction will be decoded, and the second instruction will be basically fetched. Then in the third cycle, the third instruction will be fetched, the second instruction is decoded, the first instruction is basically executed, and so on. Remember, with no pipelining, each one of these instructions will take 5 cycles. But now look, it will take less for sure. Let's take an example, a practical example. Here we have 5 independent instructions. These instructions doesn't depend on each other, so they can run in parallel. So in the first cycle, we fetched the first instruction. In the second cycle, we're gonna decode the first instruction. So the fetch circuit is free now, so we can fetch the second instruction. In the third cycle, we execute the first instruction, so the decoding circuit becomes free, so we can decode the second instruction. At the same time, the fetch circuit become free, so we can fetch the third instruction, and so on. If you don't have pipelining, these 5 instructions will consume 25 cycles. But with pipelining, it's now only 9 cycles. This is cycle 1, and the last instruction executed or finished at cycle 9. So only 9 cycles. So the speed up here is basically 25 divided by 9, which is 2 something, which is very good. But as I said, it's not that not that perfect, and you might have what's called hazards. There are many hazards. We're gonna explain in this lecture 2 of them, or 2 kind of issues basically that you might have that will reduce the speed up. So the first one is called branch hazard, and the second one is called data hazard. Okay, and these hazards basically make stalls. Stalls is basically called also bubbles, which is cycles with no operation, and that will reduce the speed up. Let's see an example. Here is an example for data dependency hazards, in which you have again 5 instructions, but this instruction now have some dependency. So for example, the first and the second instructions are independent. This is move AL82, this is using AL, the second one is use BL. So the pipelining will run smoothly, no problem at all. But then the third instruction, sub BL and AL, which is basically BL equal to BL minus AL, is dependent on both BL and AL. And remember, in instruction 1 and 2, will change AL and BL. And remember also that the update of the registers happens in the write back stage. So here, for example, in the 5th cycle, AL will be updated because of the first instruction, and in the 6th cycle here, BL will be updated for the first time in that program because it will be updated frequently after that. So when we do the sub BL and AL, we can fetch it normally at the 3rd cycle, because at that time the second instruction would is now in decoding stage, so the fetch circuit is free, so we can fetch it. But we can make the decoding, execution, and the memory write back only at the beginning of the 7th cycle. And remember, BL will be updated again because of the 3rd instruction at cycle number 10. And if we look at the fourth instruction now, it's again dependent on the third instruction, because it will increment BL. So in that case, we must also, wait for the 10th cycle to do the fourth instruction. But luckily enough here, the fetch can be done in the 7th cycle, because the 7th cycle, the third instruction leaves the fetch circuit free, of course, and go to the, the decoding circuit. So we have here 3 stalls or 3 bubbles. Different books use different terms, but all of them are the same, or hazards, whatever you like. Okay, we have another 3 bubbles here. Okay, and again, then at cycle 14 again, BL will be incremented, so BL will be updated again in cycle 14 for the 3rd time. Finally, move AL BL. This is basically EL equal to L plus BL. So this is dependent on AL, but remember AL finished already updates on cycle 5, which is okay. But BL, again, this is dependent on that guy and that guy. Okay, so BL finished the updates on cycle 5. BL will finish update its 3rd update on cycle 14. So we can fetch again on cycle 11, but we're gonna have 3 stalls. Then we can do the decode execute memory write back for the 5th instruction here. Okay. So without pipelining, we have totally 25 cycles, clock cycles, to execute these 5 instructions. But now, because of the data hazard or data dependency, or the issues we have here in the bubbles, okay, we have only 18 cycles. So we started at cycle 1 and we finished at cycle 18. And the speed up now is 25 divided by 18, which is, one something. Here is the second, way of introducing, hazards or stalls or bubbles into the pipeline, but now it's because of branching. So branching basically is a jump instruction, like jump 0, jump not 0. So all these jump instructions can make hazards into or bubbles into the pipeline. So to explain why, I'm gonna explain with a code, an example. So in that example here, we are assuming that AL has 8 just before the execution of that code. Okay, then we're gonna see how this code will introduce branching hazards or branching bubbles or stalls into the pipeline. Actually, this code has both data hazards and branch or jump hazards, or stalls or bubbles. So let's start by the first instruction, sub AL and 8, which is basically AL equal to AL minus 8. And in that case, it will be 0 because AL before that, as we're assuming, is equal to 8. So 8 minus 8 is 0. Good. Now for the second instruction, it can be fetched, at the second cycle, just like normal pipeline, but then we cannot, execute it until the 5th cycle, because we need to know if we're gonna jump or not. I'm saying here jump 0. Jump 0 means if the 0 flag is 1, jump to the line with the label high. So that's why we need to wait until the 5th cycle, because at the 5th cycle here, AL will be updated and also the flag register will be updated. In the write back again, we update the flags, all the registers, including the flag register, at the end or at the write back stage. That's why I made the decode execute memo write back just at the starting from cycle 6. And we have here 3 bubbles, but these are because of the data dependency. So between instruction 1 and instruction 2, there is data dependency or data hazard. Now, can we fetch, the third instruction at cycle 6? Because the second instruction now basically in the decode stage. And the answer is that's basically the type of uncertainty in which we cannot do such operation, basically by blinding. Because if we really gonna jump, we will not execute this instruction and we gonna jump directly to high move BL and 8. So why we fetch it? So that's not true. And if we don't jump, we're gonna execute it, then execute the second one. So we need to know if we're gonna jump or not. That's why we cannot do the by blinding for the third instruction, because we are not sure if we're gonna execute it. And we're gonna know this by the end of the execution of the second instruction, jump 0 high, basically at the 9th cycle when we do the write back. Okay, so only at that time we're gonna know if we're gonna execute or not. And of course, in that case here, since AL is 8, that's why I choose this assumption. I made this assumption that AL is 8 before the execution of that code. So 8 minus 8 is 0. So the 0 flag will be 1, really 1. And we're gonna do the jump. So that's why here we do that, the fetch of the last instruction, the fourth instruction. And we have again, bubbles here. But these bubbles now between the second and the fourth instructions is branch hazard or branch hazard or bubbles. We can better write them here. One may say there is a dependency between the fourth and the third instruction. I'm gonna say no, because basically here you have, either one of them will be executed because of the jump. Okay, if there is no jump, of course there will be, if there is no jump, of course there will be a dependency between the fourth and the third, instruction. Okay, but we don't have this right now, so we just have, the branch hazard. Okay, guys. So basically here, there is still a speed up, and the speed up again. Here you executed 3 instructions. This 3 instruction takes, should take 15 cycles, but now you execute them in 10 cycles. So 1.5, 1.5 speed up. Okay. So just, to give you some information, there is some techniques called the branch prediction, which improves the efficiency of the processor by trying to predict if this, branch will be taken or not taken. Okay, and based on the speculation, we can really fetch, or make good speculation or good, prediction on the way or the instructions that is going to be fetched. But it's out of the scope of that course to explain the, the details of this branch, because it's really complicated. It's not that easy. Okay, guys, that was it for, the pipelining. Thank you very much for watching, and see you in the next video. Bye-bye.